Hi, I'm Inge Verboven, and as a PhD student, I'm focusing on organic light-emitting diodes. These light-emitting devices are composed of very thin nanometer ranged layers. And that being said, the most commonly used thin film deposition technique is spin coating. This lab-scaled application technique can deposit continuous and homogeneous layers from a few nanometers up to a few micrometers, but mostly used are layer thicknesses between 10 and 100 nanometers. Let's have a look how this technique works.
Firstly, a flat substrate is placed in the center of the horizontal rotating sample holder and held in position by a small vacuum underneath the sample. The solution is dispensed in the center of the substrate until the surface is completely covered. The sample holder is then rotated at high speed and acceleration. Under influence of the centrifugal forces, a smooth and uniform thin film is formed. The final film thickness and other properties of the layer will depend on the nature of the solution, like the viscosity, the drying rate, the percent solids, and the surface tension, and on the choice of spin coating parameters such as the final rotational speed, the acceleration, and the spin time. 4 stages of the spin coating process can be distinguished. In the first stage, the fluid is deposited onto the substrate surface. There are 2 common methods of dispense. The first method is a static dispense, where the fluid is simply deposited in the center of the substrate. The second method is dynamic dispense, where the fluid is deposited on an already slowly rotating substrate. The second stage is started when the substrate is accelerated up to a desired rotational speed. During this rotation, spiral vortices are formed as a result of the twisting motion caused by the inertia of the top of the fluid layer, while the substrate below rotates faster and faster. In the third stage, the substrate is spinning at a constant rate and fluid viscous forces dominate the fluid thinning behavior. Edge effects are often seen because the fluid flows uniformly outwards and it forms droplets at the edge that are flung off the substrate. The fourth and last stage occurs when the solvent evaporation dominates the coating thinning. At this point, the coating is effectively transformed into a layer. Usually, higher rotational speeds and longer spin times create thinner films. Now let's see what this technique looks like in real life when we spin coat the conductive polymer PSS onto a ITO pattern glass substrate.
To conclude, spin coating is a widely spread and very fast lab-scale deposition technique that is capable of coating very thin homogeneous layers. But unfortunately, it's not suited for continuous manufacturing. Only 10% of the spin-coated solution forms the actual layer, which means the other 90% is waste. Also, the use of this technique for industrial purposes is somewhat limited due to the restricted choice in substrate. A substrate has to be small, squared, rigid, and flat, and due to the restricted choice in materials.